There is a heartbeat older than memory, older than the first human footprint on sand, older, even, than the continents themselves. It is the pulse of the ocean, a rhythm so vast, so patient, that it seems almost to exist outside of time. If you've ever stood at the water's edge in the hours before dawn, when the world is hushed and the boundary between sea and sky dissolves into silver mist, you felt it. That presence, that ancient, wordless knowing that something immense is breathing beneath the surface. The tides rise. The tides fall. They have done so for billions of years, long before there were eyes to witness them, long before there were minds to wonder why. And yet, for all our science and exploration, for all our satellites and submarines, the ocean guards its deepest secrets jealously. We've mapped the surface of Mars with greater detail than we've charted our own seafloor. We've sent probes to the edge of the solar system, yet more than 80% of Earth's ocean remains unexplored, unmapped, unseen by human eyes. Tonight, we journey into those mysteries, not with bright lights and loud machinery, but with quiet curiosity and patient observation. We'll trace the invisible threads that connect the moon above to the waters below. We'll walk the shores where ancient peoples first noticed patterns in the chaos, patterns that seem to whisper of divine intention, of cosmic order hidden just beneath the surface of everyday experience. We'll descend into depths where sunlight has never reached, where creatures glow with their own cold fire, where the pressure would crush human bones like paper. But we begin here, at the threshold, at the place where water meets land, where the known world touches the unknown. Because it is here, in the tidal zones, that the ocean's mysteries first reveal themselves. It is here that the celestial and the terrestrial meet in an embrace that has shaped not just coastlines, but consciousness itself. Every civilization that has risen beside the sea has felt the pull of these mysteries. Every sailor who has ventured beyond sight of land has carried questions into the blue immensity, and not all of those questions have found answers. What moves the sea? What lies in the unmapped depths? Why do tides seem to breathe with such regularity, such purpose? And what secrets might the ocean hold about the origins of life itself, about the nature of time, about forces we can measure but never truly see? These are not new questions. They are as old as human wonder, as persistent as the waves themselves. But they are questions worth asking again, slowly, in the quiet hours when the boundary between waking and dreaming grows thin. Because in seeking answers, we find something more valuable than facts. We find connection. We find our place in the vast, turning machinery of the cosmos. We find, perhaps, a kind of peace in knowing that we are part of something so much larger than ourselves. So settle in. Let the sound of distant waves become the soundtrack to this journey. Let your breathing slow to match the rhythm of the tides, that ancient pulse that has been beating since before the first dawn and will continue beating long after the last sunset. The ocean is waiting. Its mysteries are patient. And tonight, for a little while, we'll listen to what it has to say. The story begins, as all ocean stories must, with those who watched and wondered first. Long before the word science existed, there were watchers, people who lived so close to the sea that the rhythm of waves became the rhythm of their lives. They noticed things, small things at first, then larger patterns, then something approaching truth. They noticed that the sea did not move randomly. It rose and fell with purpose, with regularity, as if following instructions from some unseen conductor. And gradually, observation became story. Story became myth. And myth became the first fumbling attempts to explain what we now call the tides. In the South Pacific, among the scattered islands of Polynesia, ancient navigators developed a relationship with the ocean that bordered on the mystical. These were people who could read the sea the way others read books, interpreting the character of swells, the behavior of currents, the taste of spray on the wind. They noticed that tides followed the moon's journey across the night sky. When the moon hung full and bright, tides swelled higher, withdrew farther. When the moon vanished into darkness, tides gentled, became more modest in their advance and retreat. The Polynesians wove this knowledge into their cosmology. The moon, they said, was a deity who commanded the waters. Some islands told of Hina, the moon goddess, who pulled at the ocean's hem like a woman drawing up the edge of a vast blue garment. Others spoke of Marama, whose face appeared in the sky each night to remind the waters of their obligations. These weren't mere stories. They were mnemonic devices, ways of encoding vital navigational information into forms that could survive generations of oral transmission. The myths were true, in their way. They captured something essential about the relationship between moon and tide. Even if the mechanism remained mysterious, halfway around the world, on the shores of ancient Greece, philosophers stood on Mediterranean beaches and contemplated similar mysteries. The Greeks loved categories, loved trying to impose rational order on the natural world's apparent chaos. Aristotle himself wrote about the tides, though the Mediterranean's relatively modest tidal ranges made patterns harder to discern than in the dramatic coastlines of the Atlantic. Still, the Greeks knew there was a connection to celestial movements. They observed, they theorized, they argued with each other in the ways philosophers do, each defending their interpretation with the fierce certainty that comes from incomplete information. Some Greek thinkers attributed tides to cosmic breathing, the universe itself inhaling and exhaling, causing waters to rise and fall in sympathy. Others proposed vast underwater rivers that periodically filled and drained the seas. A few, more accurate than they knew, suggested the moon's influence, though they couldn't explain how a distant celestial body might physically affect terrestrial waters. The mechanism eluded them, but the correlation did not. They were groping toward truth in the darkness. And sometimes their hands touched something real that in ancient Egypt, where the Nile's flooding governed agricultural cycles and the survival of civilization itself. Priests maintained meticulous records of water levels. The Nile didn't experience ocean tides, it was too far upstream, but the concept of cyclical water movement was central to Egyptian cosmology. The god Hapi was said to dwell in caverns at the source of the Nile, periodically releasing waters that would inundate the valley, bringing life-giving silt to the fields. This mythological framework helped Egyptians predict and prepare for annual floods, just as tide watchers elsewhere learned to predict the sea's movements. But perhaps no culture developed a more intimate, practical understanding of tides than the coastal peoples of northwestern Europe, the Celts. The Norse, the tribes who inhabited the shores of Britain and Scandinavia. These were places where tidal ranges could be dramatic, where the difference between high and low water might exceed 30 or 40 feet in certain harbors and inlets. Here, misreading the tides could mean death. A ship caught on the wrong side of a tidal bar could be stranded for hours, vulnerable to weather, raiders, or simply the crushing exposure when the tide retreated and left wooden hulls resting on rocks. The Vikings, those master sailors who somehow crossed the North Atlantic in open boats, were also master tide readers. They couldn't explain why tides behaved as they did, but they knew the patterns with intimate precision. They knew which channels would be passable at which times. They knew when tidal currents would assist their journeys and when those same currents would become impassable barriers. They encoded this knowledge in their sagas and navigational lore, knowledge that was simultaneously practical and sacred, the kind of information that kept people alive in an unforgiving environment. Celtic Druids in Britain performed ceremonies tied to tidal cycles, particularly during the extremes of spring tides when the moon was full or new. These weren't superstitions in the modern sense. They were acknowledgments of pattern, recognitions that human activity needed to align with natural rhythms. The word tide itself comes from Old English, originally meaning time or season. The tides were time itself, made visible, given physical form as advancing and retreating water. What unites all these ancient watchers, Polynesian navigators, Greek philosophers, Egyptian priests, Viking sailors, Celtic Druids, is a shared recognition that the sea possessed agency, possessed rhythm, possessed something approaching intention. They didn't understand gravity. They didn't have the mathematics to calculate gravitational forces or predict tidal heights with precision. But they understood, in a deep and embodied way, that the ocean was responsive, that it listened to something, that it followed rules, even if those rules were written in a language humans couldn't yet read. They stood at the edge of understanding, these ancient observers. They asked the right questions, even when the answers remained beyond reach. They noticed the moon's correlation with tides, even without understanding the mechanism. They watched the sea rise and fall with such regularity that they knew, intuitively, that this was not chaos. This was order. This was meaning, and slowly, generation after generation, their observations accumulated. Their stories encoded truth. Their myths preserved pattern. Until finally, centuries later, someone would arrive with the mathematics and instruments to reveal what those ancient watchers had always suspected, that the moon was indeed commanding the waters, reaching across empty space with invisible hands, pulling at the ocean with forces we now call gravity. But we're getting ahead of ourselves. First, we must understand what those invisible hands actually do, how they work, why they create the specific patterns we call tides. The ancient watchers saw the effects. Now it's time to understand the cause. Picture the moon tonight, not as a romantic backdrop or a poet's symbol, but as what it truly is, a massive sphere of rock, roughly 1/4 Earth's diameter, orbiting our planet at an average distance of 240,000 miles. It has no light of its own. What we see is reflected sunlight, the sun's fire bouncing off ancient lunar dust and traveling back to Earth to illuminate our nights. The moon is cold, airless, dead in the biological sense. And yet, it moves oceans. How? The answer is almost absurdly simple, which is perhaps why it took humanity so long to discover it. The moon pulls. That's all. It pulls on Earth with the force we call gravity, the same force that makes apples fall and keeps planets in orbit. Every object with mass attracts every other object with mass. The strength of that attraction depends on two factors: how massive the objects are and how far apart they sit. The moon is massive, not as massive as Earth, but massive enough. And while 240,000 miles seems like an enormous distance, in cosmic terms, it's practically nothing. We're close neighbors, Earth and moon. We've been dancing together for over 4 billion years, locked in a gravitational embrace that shapes both our worlds. But here's where the magic happens, where the science becomes almost poetic in its elegance. The moon doesn't pull on Earth uniformly. It can't, because gravity weakens with distance, and different parts of Earth are different distances from the moon. The side of Earth facing the moon is about 8,000 miles closer to it than Earth's center. And Earth's center is about 8,000 miles closer than the far side. Those differences matter. The water on the near side feels a stronger gravitational pull toward the moon than Earth's solid center does. The center feels a stronger pull than the water on the far side. This difference in gravitational force, this gradient, is what we call tidal force. And it's what makes tides possible. Imagine the moon reaching down with invisible fingers, touching the ocean on the side facing it, pulling that water into a subtle bulge. Not a huge bulge. In the open ocean, maybe 2 or 3 feet higher than average, but a real, measurable elevation of water, drawn toward the moon like iron filings toward a magnet. Now comes the beautiful, slightly mind-bending part. While the moon is pulling the near-side water toward it, it's also pulling on Earth itself, the solid rock and metal at the planet's center. And because the center is farther from the moon than the near-side water, it feels a slightly weaker pull. So Earth itself is being drawn toward the moon, but not quite as strongly as the water on the near side. The result? The near side water bulges toward the moon. But what about the far side? Logic might suggest that the water on the far side, being farthest from the moon, would be left behind, right? And that's exactly what happens. While Earth's center is being pulled toward the moon, the far side water, being even farther away, feels an even weaker pull. So it gets left behind as Earth is drawn moonward. The far side water bulges outward, away from the moon, not because it's being pushed, but because it's being left behind as the rest of the planet is pulled slightly toward the moon. The result is beautiful in its symmetry. 2 bulges of water on opposite sides of Earth. One facing the moon, pulled toward it. One on the far side, left behind. Earth, with its oceans, becomes slightly elliptical, stretched along the line connecting Earth and moon, compressed slightly along the axis perpendicular to that line. Now at Earth's rotation. Our planet spins on its axis once every 24 hours, carrying continents and oceans through these tidal bulges. As your location rotates into a bulge, you experience high tide. Water levels rise along your coast. About 6 hours later, your location has rotated 90 degrees, and you're between the bulges. Low tide. 6 hours after that, you've rotated into the second bulge, high tide again, then low tide once more, and the cycle continues, twice daily, as reliable as sunrise, as predictable as the stars wheeling overhead. There's something almost meditative about understanding this. The ocean isn't choosing to rise and fall. It's not conscious, not willful. It's simply responding to forces, fundamental forces that govern how masses interact across space. The moon pulls, Earth spins. Water, being liquid and mobile, responds to these forces in ways that solid land cannot. The result is tides, the ocean breathing under lunar guidance, rising toward the moon and away from it simultaneously, creating rhythms that have persisted for billions of years. And those rhythms have shaped more than coastlines. They've shaped life itself. Because in the beginning, when Earth was young and life was just emerging from primordial chemistry, the moon was much closer than it is now, perhaps half its current distance. Tides then would have been enormous, dramatic, powerful enough to flood vast stretches of coastline and then retreat, leaving behind tidal pools where organic molecules could concentrate, where the boundary conditions between wet and dry, between ocean and atmosphere, created opportunities for complexity to emerge. Some scientists believe these ancient tides were crucial to the origin of life, that the rhythmic wetting and drying, the concentration of chemicals, the energy provided by tidal motion, all of this created environments where the first self-replicating molecules could form. If this hypothesis is correct, then we owe our very existence to tides, to the moon's gravitational command, to the fact that Earth happened to have a large satellite pulling at its oceans in regular, predictable cycles. The moon, in this light, becomes more than a celestial neighbor. It becomes a gardener, tending the conditions that allowed life to root and grow. Its silent command, operating through the invisible medium of gravity, sculpted the environments where chemistry became biology, where molecules became cells, where the first fragile threads of life began their journey toward the magnificent complexity we see today. But the moon doesn't work alone. There's another player in this celestial drama, another massive body whose gravity also reaches Earth and contributes to the tidal dance. The sun, our star, vastly larger than the moon but also vastly farther away, adds its own gravitational voice to the chorus. And when sun and moon work together, aligning their poles, the tides respond with even greater drama. The dance, already beautiful, is about to become sublime. That if the moon were the only celestial body affecting Earth's tides, the ocean's rhythm would be simpler, predictable in a straightforward way, following the moon's monthly journey with consistent regularity. But the universe is rarely simple, and Earth, as it turns out, has two choreographers guiding its tidal performance: the moon, close and commanding, and the sun, distant but immensely powerful. The sun is massive, about 27 million times more massive than the moon. By rights, with that much mass, it should dominate Earth's tides completely, overwhelming the moon's influence. But here's where distance saves the day. The sun sits roughly 93 million miles away, about 400 times farther from Earth than the moon is. And because gravitational force weakens with distance, specifically with the square of the distance, that enormous gap in distance matters more than the enormous gap in mass. The result? The sun's tidal force on Earth is real, measurable, and significant, but it's only about 46% as strong as the moon's. The moon remains the primary conductor, but the sun plays second violin, adding harmonies and depth to the composition. And when these two celestial bodies align, their efforts, when they pull on Earth from the same direction, or from opposite directions, their combined gravitational forces create tides that are markedly stronger than average. This happens twice each lunar month, during specific lunar phases that ancient watchers noticed long before they understood the mechanism. The first occurs during the new moon, when the moon sits between Earth and sun. From our perspective, the moon is invisible. Its shadowed side faces us, lost against the brightness of the day sky. But gravitationally, this is a moment of perfect alignment. Sun, moon, and Earth form a straight line, with the moon in the middle. The sun and moon are pulling in the same direction, their gravitational forces combining, amplifying each other's effects. The second alignment occurs during the full moon, when Earth sits between the sun and moon. The sun illuminates the moon's entire face, making it appear as a perfect circle in the night sky. From a gravitational perspective, sun and moon are now pulling from opposite sides of Earth. But remember the tidal bulges, one toward the moon, one away from it. When the sun and moon pull from opposite directions, they're both contributing to these same bulges, reinforcing them, making them higher. That we call these enhanced tides spring tides, though the name has nothing to do with the season. The term comes from the Old English word springon, meaning to leap up or to well forth, a perfect description for tides that seem to surge with extra energy. During spring tides, high tides climb higher up the beach than usual. Low tides retreat farther, exposing rock formations and tidal zones that normally remain submerged. The difference between high and low water, the tidal range, can be 50% greater during spring tides than during average conditions. If you've ever planned a beach visit around tide times, you felt the effects of spring tides, even if you didn't know the term. That day when the high tide seemed to reach unusually far, flooding areas of the beach that were dry just hours before, that was likely a spring tide. That morning when the low tide retreated so far you could walk to rock formations normally accessible only by boat, spring tide again. These are the dramatic moments in the tidal cycle, when the ocean seems most alive, most dynamic, most responsive to the celestial forces shaping it. But the celestial alignment doesn't always cooperate. 1 week after the new moon, the moon reaches its first quarter phase. From Earth, it looks like a half circle, as though someone sliced the moon down the middle. But the true significance isn't visual, it's geometric. During quarter moons, the sun and moon form a 90-degree angle with Earth at the corner. They're pulling at cross purposes now, their gravitational forces partially canceling each other out. During a full moon or new moon, when sun and moon align, imagine them both pulling on the same tidal bulge, amplifying it. During quarter moons, the sun is trying to create its own tidal bulge at a 90-degree angle to the moon's bulge. The result is a compromise. The ocean's response to these competing forces creates tides that are less extreme than average. We call these neap tides, from an Old English word meaning barely touching or barely sufficient. During neap tides, the difference between high and low water shrinks, sometimes by half compared to spring tides. High tides don't climb as far. Low tides don't retreat as dramatically. The ocean seems to be taking a rest, a brief pause between the more energetic spring tides. Coastal harbors that become difficult to navigate during spring tide low waters remain accessible during neap tides. Tidal currents, which can be powerful and dangerous during spring tides, gentle during neap tides, becoming more manageable for small boats and swimmers. This cycle, from spring tide to neap tide and back to spring tide, takes about 2 weeks, following the moon's phases from new to full and back again. It's a rhythm within a rhythm, a longer beat underlying the daily pulse of high and low tides. And it means the character of the ocean is constantly changing, evolving through this fortnightly cycle. The beach you visit today will behave differently from the beach you visit next week, and differently still from the beach 2 weeks from now. But there's yet another layer to this celestial choreography, another subtlety that adds complexity to the dance. Neither the moon's orbit around Earth nor Earth's orbit around the sun is a perfect circle. Both are ellipses, meaning the distances between these bodies change throughout each cycle. When the moon is at perigee, its closest approach to Earth, its gravitational effect is strongest. When it's at apogee, its farthest point, the effect weakens. Similarly, Earth is closest to the sun in early January and farthest in early July, causing seasonal variations in the sun's tidal contribution. When a spring tide happens to coincide with lunar perigee, the result is what some call a perigean spring tide, or more colloquially, a king tide, the highest tides possible, when the ocean seems to swell beyond its usual bounds. These extreme tides can cause coastal flooding in low-lying areas, can breach defenses designed for average conditions, can remind us that the forces shaping tides are immense, powerful, and ultimately beyond human control. The beauty of this system, this interplay of moon, sun, Earth's rotation, elliptical orbits, and phase alignments, is that it remains completely predictable despite its complexity. Modern tide tables can tell you with remarkable precision when high and low tides will occur at any coastal location, months or years into the future. This knowledge, built on centuries of observation and refined by mathematical models, has made coastal navigation safer, has helped communities prepare for extreme tides, has allowed us to plan our interactions with the ocean with unprecedented precision. But knowing when tides will occur is only part of the story. Because once these celestial forces generate tides in the open ocean, those tides must travel to shore. And as they do, they encounter Earth's actual geography, the varied topography of continental shelves, the shapes of bays and estuaries, the depths and contours of underwater landscapes. What happens next transforms the relatively modest tides of the deep ocean into phenomena ranging from barely noticeable to genuinely spectacular. The shoreline has secrets of its own to reveal, and those secrets are written in the ancient language of water, stone, and timed in the deep ocean. Far from any land, tides are gentle affairs. If you were floating in the middle of the Pacific, watching the water level around you, you'd see it rise and fall by only 2 or 3 feet during a complete tidal cycle. The gravitational bulges created by moon and sun are real, but spread across such vast expanses of water, they're subtle, easily missed if you weren't actively looking for them. But something extraordinary happens when this tidal energy encounters the edge of continents. As the traveling wave of elevated water, this pulse generated by gravitational forces in the deep ocean, meets underwater slopes, coastal shelves, and the complex geometry of shorelines, it transforms. The energy that was distributed across thousands of miles of open sea suddenly concentrates, amplifies, and sculpts itself according to the specific shape of each coast. Every bay, every inlet, every stretch of shore develops its own tidal personality, unique and distinctive, shaped by the hidden geometry beneath the waves. Consider the Bay of Fundy, cradled between New Brunswick and Nova Scotia in Canada's maritime provinces. Here, tides don't just rise and fall, they surge and retreat with an energy that borders on violence. The Bay of Fundy regularly experiences tidal ranges exceeding 50 feet, the highest tides recorded anywhere on Earth. Twice each day, approximately 160 billion tons of water flood into this bay, creating a temporary inland sea where mudflats existed just hours before. Then the tide turns, and that enormous volume of water drains away, revealing a landscape utterly transformed, boats resting on exposed seabed, cliffs of mud carved with intricate patterns, an alien geography that exists only during the brief windows between tides. What makes Fundy so extreme? The answer lies in its shape and proportions. The bay is roughly funnel-shaped, wide at its mouth where it opens to the Atlantic, then narrowing progressively toward its inland head. As the tidal wave enters through the wide mouth, it carries an immense volume of water. But as the bay narrows, that same volume gets forced into an increasingly confined space. The water has nowhere to go but up. Additionally, the bay's length, roughly 180 miles, and its average depth create what physicists call a resonance effect. The natural period of water sloshing back and forth in the bay very nearly matches the tidal period. This creates reinforcement, like pushing a child on a swing at exactly the right moment with each oscillation, amplifying the movement to heights far beyond what you'd achieve with a single push. The result is mesmerizing. Watching the tide come into the Bay of Fundy is like watching a force of nature that seems too large to be real. You can see the water level rising, not metaphorically, not through abstract measurements, but visibly, obviously, dramatically. The tide doesn't creep in. It charges, filling channels, flooding tidal flats, making the very landscape seem temporary and negotiable. Rocks that were 15 feet above water level an hour ago now have waves breaking over them. Beaches disappear. The entire relationship between land and sea rewrites itself every 6 hours. Travel south along the Atlantic coast to the Bay of Mont Saint-Michel in Normandy, France, and you'll encounter another tidal extreme, though of a different character. Here, the tidal range can exceed 40 feet during spring tides, but what makes Mont Saint-Michel remarkable isn't just the height of the tides, it's the speed. The bay fronting this medieval abbey features an exceptionally flat coastal plain. When the tide comes in, It advances across this flat expanse with startling rapidity. The famous saying is that the tide comes in faster than a galloping horse. While that's romantic exaggeration, the tide does advance quickly enough to be dangerous. People have been caught and drowned by misjudging the tide's speed, finding themselves cut off from shore by water that seemed distant moments before. The island of Mont Saint-Michel itself becomes truly isolated during high tides. Surrounded completely by water, accessible only by the modern causeway that now connects it to the mainland. For centuries, pilgrims timing their visits poorly could find themselves stranded, waiting hours for the tide to retreat enough to make the journey to shore. The tide here isn't just a natural phenomenon. It's an active participant in the location's history, mythology, and continuing appeal. But not all extreme tides manifest as dramatic ranges. Some reveal themselves as tidal currents, powerful flows of water that surge through narrow channels with each tidal change. The Saltstraumen in Norway is perhaps the world's most powerful tidal current, a narrow strait where billions of gallons of water rush through with each tide, creating whirlpools, standing waves, and currents that can exceed 20 miles per hour. The sound alone is remarkable, a roar of moving water, a constant churning that speaks to forces operating on a scale difficult to comprehend. Fishermen know the Saltstraumen well. The powerful currents stir nutrients from the seafloor, creating rich feeding grounds that attract massive schools of fish. But fishing these waters requires intimate knowledge of tidal timing. The currents are too powerful to navigate during peak flow. Attempting to cross at the wrong time could capsize boats, could sweep vessels miles off course. So fishing happens during the brief windows of slack water between tidal flows, when the current pauses, takes a breath, before reversing direction. It's a dance of timing, a negotiation with forces far more powerful than any boat or motor. These dramatic locations, Fundy, Mont Saint-Michel, Saltstraumen, represent extremes. But they illustrate a universal truth. Tides are profoundly local. The same gravitational forces that pull on water in the Bay of Fundy also pull on water in the Caribbean, in the Mediterranean, in the Pacific Islands. But the results are entirely different, sculpted by the specific geometry of each location. Shallow, broad continental shelves amplify tides. Deep water close to shore dissipates tidal energy. Funnel-shaped bays concentrate it. Wide, open coastlines spread it out. The Caribbean Sea, surrounded by islands and partially enclosed by continental masses, experiences microtides, changes so subtle they're often overshadowed by wind and weather effects. A Caribbean beach might see tidal ranges of only a foot or two, barely noticeable compared to the dramatic changes in places like Fundy. The Mediterranean Sea, nearly landlocked with only the narrow Strait of Gibraltar connecting it to the Atlantic, experiences even more modest tides. For ancient Mediterranean peoples, tides were curiosities rather than dominant features of coastal life. Yet even in these places of modest tides, the ocean still breathes. The changes are gentle, almost imperceptible, but they're real, and they're evidence of the same gravitational conversation happening everywhere. The same moon pulling, the same sun adding its contribution, the same fundamental forces operating according to laws that don't change from place to place, that connect every shoreline in the world into a single, unified system. And these forces don't just shape water, they shape land itself. Slowly, patiently, over timescales that make human history seem like an eye blink. Tidal erosion carves cliffs, sculpts rock formations, creates caves and arches. The constant advance and retreat of water, twice daily, year after year, millennium after millennium, acts like a patient sculptor, wearing away resistance, revealing the hidden structures within stone. Coastal landscapes owe their forms not just to wind and rain and rivers, but to tides, to the moon's gravitational persistence, shaping Earth's surface through the medium of moving water. But the ocean's secrets don't end at the shoreline, don't exhaust themselves in the mechanics of tides. Because beneath all this, beneath the surface waters that rise and fall, beneath the continental shelves and tidal currents, lies a realm vast beyond imagination. A realm we've barely begun to explore. A realm where mysteries multiply the deeper you descend, where life exists in forms that seem alien. where the very nature of the sea becomes strange, unknown, and beautiful in ways that challenge our understanding of what's possible on this planet. The creatures who inhabit these hidden depths, who live by rhythms stranger than the tides, are waiting to share their stories. There's a border between worlds that shifts position twice a day. It's not marked on any map, not fixed in any permanent way, but it's as real as any boundary on Earth. This is the intertidal zone, the narrow band of coastline that spends part of each day underwater and part exposed to air. It's a harsh place, a demanding place, perhaps the most challenging environment on the planet for anything trying to make a living. And yet it teems with life, because wherever conditions are difficult, wherever survival requires adaptation and ingenuity, evolution responds with creativity. And the intertidal zone has been a crucible of evolution for hundreds of millions of years, producing organisms whose very biology is written in tidal rhythms, whose life cycles are synchronized to the moon's phases, whose daily routines follow schedules set not by sunlight, but by the gravitational pull of a celestial body 240,000 miles away. Consider the barnacle, that small, cone-shaped creature that cements itself to rocks so firmly that attempting removal will break the rock before breaking the barnacle's grip. Barnacles live their adult lives glued in place, unable to move, unable to flee danger or seek food. They must survive wherever they first settled, which means they must be prepared for radical environmental changes. Twice a day, as the tide retreats, barnacles find themselves exposed to air, to sun, to predatory birds and other creatures that can't reach them underwater. Their solution is elegant. As the water recedes, barnacles seal themselves inside their shells, closing trapdoors made of overlapping plates that create an almost watertight chamber. Inside this tiny sealed space, a film of water preserves moisture, allows minimal respiration, keeps soft tissue alive despite the harsh conditions outside. The barnacle becomes a fortress, waiting, barely breathing, enduring. But when the tide returns, when water once again covers their rocky homes, the barnacles open. They extend feathery appendages called cirri, modified legs that sweep through the water like graceful fingers, filtering plankton and organic particles. For the hours of high tide, the barnacle feeds frantically, gathering enough nutrition to sustain itself through the next low tide period. Its entire existence is choreographed by the tides, waiting, feeding, waiting again, in an endless cycle that has continued for generations beyond counting. Or consider the hermit crab, that endearing wanderer who carries a borrowed shell on its back. Hermit crabs face a unique challenge. They inhabit a world that completely transforms twice daily. During high tide, they forage underwater, using their gills to extract oxygen, searching among seaweed and rocks for food. But as the tide retreats, they must find a tide pool, a pocket of water left behind by the receding ocean, or risk desiccation and death. Watch a hermit crab navigate this challenge. And you're watching instinct refined across millions of years. They seem to understand tide timing innately, beginning their journey back to deeper water or protected pools well before the water level becomes critical. They've internalized the rhythm, made it part of their neurology. The moon's gravitational pull has, through evolutionary time, written itself into the hermit crab's behavior. Ghost crabs present an even more remarkable adaptation. These pale, sand-colored crustaceans live primarily on land, digging burrows above the high tide line. But they breathe with gills, requiring periodic wetting to extract oxygen. So ghost crabs must balance their terrestrial lifestyle with regular trips to the surf to moisten their gills. They time these moisture-gathering expeditions according to tidal cycles. During extreme low tides, when the water is farthest away, ghost crabs venture greater distances from their burrows, taking advantage of the expanded beach to forage. During high tides, especially at night, they hunt along the water's edge, scavenging whatever the ocean has delivered. But the moon's influence extends far beyond the visible intertidal zone. Out on coral reefs, in tropical waters where tides may be modest, lunar timing still governs one of nature's most spectacular reproductive events: coral spawning. Many coral species reproduce only once a year, and they do so synchronously, all individuals of a given species releasing their eggs and sperm at precisely the same time. This coordination is essential. Corals are sessile. They can't move to find mates. Their only hope for genetic mixing is to release gametes into open water and trust that currents and chance will bring eggs and sperm together. But random release would mean most gametes would simply disperse, never finding their counterparts. So corals have evolved to synchronize their spawning to specific environmental cues: water temperature, day length, and crucially, the lunar cycle. On certain nights, typically following full moons, during spring tides, entire reefs release their gametes simultaneously. Billions of eggs and sperm float toward the surface in an underwater snowstorm, a blizzard of potential life that turns the water milky. This mass spawning, this coordinated release triggered by the moon's phase and tidal timing, is essential for reef reproduction and genetic diversity. The mechanism by which corals sense lunar phases remains somewhat mysterious. They don't have eyes, don't have brains in any conventional sense. Yet somehow, coral polyps detect the cycle, respond to it, time their reproduction with precision. The moon, through some combination of light levels and tidal cues, communicates with life that seems too simple to be listening. In mangrove forests, those remarkable intertidal ecosystems where trees grow with their roots in salt water, the tide orchestrates everything. Young fish, shrimp, and crabs by the millions use mangrove roots as nurseries, seeking shelter among the tangled complexity during high tides when these areas are flooded. The Saltstraumen in Norway is perhaps the world's most powerful tidal current, a narrow strait where billions of gallons of water rush through with each tide, creating whirlpools, standing waves, and currents that can exceed 20 miles per hour. The sound alone is remarkable, a roar of moving water, a constant churning that speaks to forces operating on a scale difficult to comprehend. Fishermen know the Saltstraumen well. The powerful currents stir nutrients from the seafloor, creating rich feeding grounds that attract massive schools of fish. But fishing these waters requires intimate knowledge of tidal timing. The currents are too powerful to navigate during peak flow. Attempting to cross at the wrong time could capsize boats, could sweep vessels miles off course. So fishing happens during the brief windows of slack water between tidal flows, when the current pauses, takes a breath, before reversing direction. It's a dance of timing, a negotiation with forces far more powerful than any boat or motor. These dramatic locations, Fundy, Mont Saint-Michel, Saltstraumen, represent extremes, but they illustrate a universal truth: tides are profoundly local. The same gravitational forces that pull on water in the Bay of Fundy also pull on water in the Caribbean, in the Mediterranean, in the Pacific Islands. But the results are entirely different, sculpted by the specific geometry of each location. Shallow, broad continental shelves amplify tides. Deep water close to shore dissipates tidal energy. Funnel-shaped bays concentrate it. Wide, open coastlines spread it out. The Caribbean Sea, surrounded by islands and partially enclosed by continental masses, experiences microtides, changes so subtle they're often overshadowed by wind and weather effects. A Caribbean beach might see tidal ranges of only a foot or two, barely noticeable compared to the dramatic changes in places like Fundy. The Mediterranean Sea, nearly landlocked with only the narrow Strait of Gibraltar connecting it to the Atlantic, experiences even more modest tides. For ancient Mediterranean peoples, tides were curiosities rather than dominant features of coastal life. Yet even in these places of modest tides, the ocean still breathes. The changes are gentle, almost imperceptible, but they're real, and they're evidence of the same gravitational conversation happening everywhere. The same moon pulling, the same sun adding its contribution, the same fundamental forces operating according to laws that don't change from place to place, that connect every shoreline in the world into a single, unified system. And these forces don't just shape water, they shape land itself. Slowly, patiently, over timescales that make human history seem like an eye blink. Tidal erosion carves cliffs, sculpts rock formations, creates caves and arches. The constant advance and retreat of water, twice daily, year after year, millennium after millennium, acts like a patient sculptor, wearing away resistance, revealing the hidden structures within stone. Coastal landscapes owe their forms not just to wind and rain and rivers, but to tides, to the moon's gravitational persistence, shaping Earth's surface through the medium of moving water. But the ocean's secrets don't end at the shoreline. Don't exhaust themselves in the mechanics of tides. Because beneath all this, beneath the surface waters that rise and fall, beneath the continental shelves and tidal currents, lies a realm vast beyond imagination. A realm we've barely begun to explore. A realm where mysteries multiply the deeper you descend, where life exists in forms that seem alien, where the very nature of the sea becomes strange, unknown, and beautiful in ways that challenge our understanding of what's possible on this planet. The creatures who inhabit these hidden depths, who live by rhythms stranger than the tides, are waiting to share their stories. There's a border between worlds that shifts position twice a day. It's not marked on any map, not fixed in any permanent way, but it's as real as any boundary on Earth. This is the intertidal zone, the narrow band of coastline that spends part of each day underwater and part exposed to air. It's a harsh place, a demanding place, perhaps the most challenging environment on the planet for anything trying to make a living. And yet it teems with life, because wherever conditions are difficult, wherever survival requires adaptation and ingenuity, evolution responds with creativity. And the intertidal zone has been a crucible of evolution for hundreds of millions of years, producing organisms whose very biology is written in tidal rhythms, whose life cycles are synchronized to the moon's phases, whose daily routines follow schedules set not by sunlight, but by the gravitational pull of a celestial body 240,000 miles away. Consider the barnacle, that small, cone-shaped creature that cements itself to rocks so firmly that attempting removal will break the rock before breaking the barnacle's grip. Barnacles live their adult lives glued in place, unable to move, unable to flee danger or seek food. They must survive wherever they first settled, which means they must be prepared for radical environmental changes. Twice a day, as the tide retreats, barnacles find themselves exposed to air, to sun, to predatory birds and other creatures that can't reach them underwater. Their solution is elegant. As the water recedes, barnacles seal themselves inside their shells, closing trapdoors made of overlapping plates that create an almost watertight chamber. Inside this tiny sealed space, a film of water preserves moisture, allows minimal respiration, keeps soft tissue alive despite the harsh conditions outside. The barnacle becomes a fortress, waiting, barely breathing, enduring. But when the tide returns, when water once again covers their rocky homes, the barnacles open. They extend feathery appendages called cirri, modified legs that sweep through the water like graceful fingers, filtering plankton and organic particles. For the hours of high tide, the barnacle feeds frantically, gathering enough nutrition to sustain itself through the next low tide period. Its entire existence is choreographed by the tides, waiting, feeding, waiting again, in an endless cycle that has continued for generations beyond counting. Or consider the hermit crab, that endearing wanderer who carries a borrowed shell on its back. Hermit crabs face a unique challenge. They inhabit a world that completely transforms twice daily. During high tide, they forage underwater, using their gills to extract oxygen, searching among seaweed and rocks for food. But as the tide retreats, they must find a tide pool, a pocket of water left behind by the receding ocean, or risk desiccation and death. Watch a hermit crab navigate this challenge. And you're watching instinct refined across millions of years. They seem to understand tide timing innately, beginning their journey back to deeper water or protected pools well before the water level becomes critical. They've internalized the rhythm, made it part of their neurology. The moon's gravitational pull has, through evolutionary time, written itself into the hermit crab's behavior. Ghost crabs present an even more remarkable adaptation. These pale, sand-colored crustaceans live primarily on land, digging burrows above the high tide line. But they breathe with gills, requiring periodic wetting to extract oxygen. So ghost crabs must balance their terrestrial lifestyle with regular trips to the surf to moisten their gills. They time these moisture-gathering expeditions according to tidal cycles. During extreme low tides, when the water is farthest away, ghost crabs venture greater distances from their burrows, taking advantage of the expanded beach to forage. During high tides, especially at night, They hunt along the water's edge, scavenging whatever the ocean has delivered, but the moon's influence extends far beyond the visible intertidal zone. Out on coral reefs, in tropical waters where tides may be modest, lunar timing still governs one of nature's most spectacular reproductive events: coral spawning. Many coral species reproduce only once a year, and they do so synchronously, all individuals of a given species releasing their eggs and sperm at precisely the same time. This coordination is essential. Corals are sessile. They can't move to find mates. Their only hope for genetic mixing is to release gametes into open water and trust that currents and chance will bring eggs and sperm together. But random release would mean most gametes would simply disperse, never finding their counterparts. So corals have evolved to synchronize their spawning to specific environmental cues: water temperature, day length, and crucially, the lunar cycle. On certain nights, typically following full moons, during spring tides, entire reefs release their gametes simultaneously. Billions of eggs and sperm float toward the surface in an underwater snowstorm, a blizzard of potential life that turns the water milky. This mass spawning, this coordinated release triggered by the moon's phase and tidal timing, is essential for reef reproduction and genetic diversity. The mechanism by which corals sense lunar phases remains somewhat mysterious. They don't have eyes, don't have brains in any conventional sense. Yet somehow, coral polyps detect the cycle, respond to it, time their reproduction with precision. The moon, through some combination of light levels and tidal cues, communicates with life that seems too simple to be listening. In mangrove forests, those remarkable intertidal ecosystems where trees grow with their roots in salt water, the tide orchestrates everything. Young fish, shrimp, and crabs by the millions use mangrove roots as nurseries, seeking shelter among the tangled complexity during high tides when these areas are flooded. The mangroves provide protection from larger predators, offer food in the form of small invertebrates, create safe havens where juvenile sea life can grow. But this service is available only during high tide. When the water retreats, the juvenile fish retreat with it, following the tide back to deeper channels. Meanwhile, terrestrial predators arrive. Birds time their feeding forays to coincide with low tides, when small fish and crustaceans are concentrated in shallow pools, easy to catch. The entire ecosystem pulses with tidal rhythm. Flooding brings one suite of species. Retreating water brings another, and the mangrove trees themselves, adapted to thrive in salt water, able to filter salt through specialized glands in their leaves, provide the structural foundation for this twice-daily transformation. Even microscopic life follows the tides. Diatoms, single-celled algae that coat mudflats with golden-brown films, possess internal clocks synchronized to tidal cycles. They migrate vertically through mud in rhythm with the tides, moving up to the surface during low tide to photosynthesize, then descending deeper as the tide rises to avoid being washed away. This vertical migration follows tidal timing so precisely that scientists can predict diatom behavior hours or days in advance just by consulting a tide table. Organisms without brains, without nervous systems, nonetheless carry within their cellular machinery the signature of the moon's rhythm. This isn't just adaptation, it's integration. These species don't merely tolerate tides. They depend on them, have organized their entire life histories around tidal rhythms. The tides aren't an external force to be endured, but an organizing principle, a predictable structure that evolution has learned to exploit. In a world where so many environmental factors are variable and unpredictable, weather, food availability, predation, the tides offer certainty. They will rise. They will fall. They will do so in patterns that repeat with clockwork precision. And life has learned to trust that certainty, to build biological strategies around it, to use the tide's predictability as a foundation for survival. This relationship between tides and life runs deeper than behavior or ecology. Some scientists argue that tides may have been crucial to life's very origins. Billions of years ago, when Earth was young and life was just beginning, the moon was much closer than today, perhaps half its current distance. Tides then would have been enormous, flooding vast stretches of coastline and then retreating, leaving behind extensive tidal pools. These pools provided unique conditions. Organic molecules concentrated as water evaporated. cycles of wetting and drying that might have facilitated the formation of primitive cell membranes, boundary conditions between ocean and atmosphere where chemistry could become complex enough to become biology. If this hypothesis is correct, and it remains speculative but intriguing, then we owe our very existence to tides, the rhythmic rising and falling of water driven by the moon's gravity may have provided the environmental staging necessary for the origin of life itself. And so the creatures of the tides carry within them an ancient inheritance, a connection to forces that transcend their individual lives, that link them to the cosmos through the intermediary of the moon. When a barnacle opens its shell as water returns, when a hermit crab times its journey to match the tide, when corals spawn under a full moon, they're participating in a conversation that has been ongoing for billions of years, a conversation between gravity and water, between the celestial and the terrestrial, between the forces that shape worlds and the fragile, persistent phenomenon we call life. But life isn't the only mystery the ocean holds. Beyond the tidal zones, beneath the surface waters where sunlight penetrates, lies a realm vast and strange beyond our everyday comprehension, a world we've barely begun to explore, where the very nature of the sea transforms into something alien, beautiful, and profoundly unknown. We've mapped the surface of Mars. We've photographed distant galaxies. We've sent robotic emissaries to the edge of our solar system and beyond. But here, on our own planet, more than 80% of the ocean remains unexplored, unmapped, unseen by human eyes. We know less about the deep sea than we do about the lunar surface. And what little we've discovered suggests that the unknown regions may harbor wonders, mysteries, and forms of life that challenge everything we thought we knew about what's possible on Earth. The deep ocean isn't just deeper water, it's a fundamentally different environment. Below about 200 meters, sunlight fades to nothing. No photosynthesis can occur. Plants cannot grow. The entire food web must operate on different principles, either consuming organic material that drifts down from the lit surface waters or finding entirely novel sources of energy. And as you descend deeper, conditions become more extreme. Pressure increases by roughly 1 atmosphere for every 10 meters of depth. At the bottom of the deepest trenches, places like the Mariana Trench, which plunges nearly 7 miles below the surface, the pressure exceeds 1,000 atmospheres. That's roughly 16,000 pounds per square inch. Enough to crush most of what we think of as solid, to compress metal, to make the very concept of emptiness or space almost meaningless. And yet, life exists there. Not just microbial life, but complex organisms, fish, crustaceans, bizarre animals that seem designed by a surrealist painter rather than by evolution. In 2019, explorers descended to Challenger Deep, the deepest known point in Earth's oceans, and filmed plastic waste resting on the seafloor. But they also filmed life, amphipods, shrimp-like creatures, actively swimming, feeding, surviving at depths we once thought impossible for complex life. One of the ocean's most beautiful mysteries resides in the depths between 200 and 1,000 meters, the twilight zone, or mesopelagic zone. Here, in the permanent dimness where only the faintest traces of surface sunlight penetrate, life has evolved to produce its own illumination. Bioluminescence, the ability of living organisms to generate light through chemical reactions, is so common in the deep ocean that it may be the rule rather than the exception. Some estimates suggest that 90% of deep-sea organisms possess the ability to produce light, but they don't all use it the same way. Some fish have light-producing organs called photophores arranged along their bodies like strings of Christmas lights, perhaps for camouflage, breaking up their silhouettes when viewed from below. Some have glowing lures dangling in front of their mouths, attracting curious prey close enough to strike. Some produce sudden flashes of light to startle predators. Some engage in bioluminescent displays that might be communication, might be mating signals, might be conversations in a language we can't yet read. The anglerfish is perhaps the most famous of these light users, or rather, the females are. Female anglerfish carry a modified dorsal spine that extends in front of their faces like a fishing rod, tipped with a glowing lure containing bioluminescent bacteria. In the absolute darkness of the deep sea, this lure is irresistible, a point of light in endless black, drawing smaller fish close enough for the anglerfish's enormous jaws to snap shut. It's a hunting strategy perfectly adapted to an evidence of journeys that ended in the depths. There are even suggestions, disputed and speculative, of structures beneath the water that don't easily fit natural explanations, arrangements of stones that some argue represent ancient human construction now submerged by rising seas. Most scientists remain skeptical, and most such claims don't withstand scrutiny. But the possibility remains intriguing. When sea levels were lower, during the last ice age, for instance, coastlines extended much farther out than today. Humans living on those now submerged coasts would have left no terrestrial record. Everything they built would now be underwater, subject to millennia of erosion, transformation, and burial. What might we find if we could search every square meter of continental shelf? The ocean doesn't easily yield its secrets. Exploration is expensive, technically challenging, and often dangerous. But slowly, incrementally, we're learning more. Autonomous underwater vehicles map previously unknown regions. Deep-sea submersibles carry cameras and sensors to the abyss. Each expedition returns with discoveries, new species, new behaviors, new understanding of how life adapts to extreme conditions, and perhaps that's fitting. Perhaps the ocean should remain, at least partially, mysterious. Perhaps we need places on Earth that resist complete knowledge, that remain wild and unknown despite our technology. The ocean reminds us that we don't understand everything, don't control everything, that there are forces and creatures and phenomena that operate according to their own logic, indifferent to human curiosity or desire. But we are not entirely separate from these mysteries. We depend on the ocean for food, for climate regulation, for the production of atmospheric oxygen. And the ocean, in turn, is affected by human activity. Which brings us to a final consideration as we approach the end of this journey: our relationship with the sea. How we've learned to live with it, depend on it, and increasingly, affect it in ways that ripple through the entire system. For as long as humans have existed, we've been drawn to the water's edge. Some of our earliest settlements grew along coastlines, beside rivers, in places where land met sea. And for good reason. The ocean provided food, transport, trade routes, and connection to distant places. But living beside the sea meant learning its rhythms, respecting its power, understanding the one force that most immediately affected coastal life: the tides. Ancient seafaring peoples, the Phoenicians, the Vikings, Polynesian navigators, Chinese traders, all developed sophisticated understandings of tides long before the scientific explanation emerged. They couldn't calculate gravitational forces or predict tidal heights using mathematics, but they could read the sea. They knew which phases of the moon brought stronger tides, which harbors would be accessible at which times, how to use tidal currents to assist voyages rather than hinder them. This knowledge was survival knowledge, passed down through apprenticeship and oral tradition, refined across generations into expertise that kept people alive and made maritime trade possible. Medieval European monasteries, many built along coasts or tidal rivers, kept meticulous tide records spanning centuries, some of the earliest systematic scientific observations in European history. These records weren't purely academic. The monasteries needed to know when supply ships could arrive, when fishing would be productive, how to manage water-powered mills that operated on tidal flow. But over time, these accumulated records revealed patterns that observation alone might miss: long-term cycles, seasonal variations, correlations with lunar and solar movements. Tidal mills represent one of humanity's earliest attempts to harness renewable energy. The concept is elegant. Construct a barrier across a tidal inlet or estuary, with gates that allow water to flow into a reservoir during high tide. When the tide falls, close the gates, trapping the water. Then release it through a controlled channel where it turns a water wheel, converting tidal motion into mechanical power for grinding grain, sawing wood, pumping water. Some tidal mills operated continuously for centuries, their schedules dictated not by human needs but by the eternal rhythm of the tides. The mills embodied a kind of wisdom we're relearning today, the recognition that working with natural rhythms is more sustainable than fighting against them. You couldn't rush a tidal mill. You couldn't demand it operate on your schedule. You had to adjust your activities to match when tidal power was available. This required patience, planning, and respect for forces beyond human control. In a sense, tidal mills were early teachers of ecological thinking, the understanding that human systems must fit within larger natural cycles. Not the reverse. Modern tidal power installations build on this ancient concept using contemporary technology. Facilities like the Siwa Lake Tidal Power Station in South Korea or the Rance Tidal Power Station in France generate substantial electricity by capturing tidal energy. Underwater turbines positioned in tidal currents function like submerged wind farms, their blades turning in response to the massive flows of water moving with each tide. The advantage of tidal power is its complete predictability. Unlike solar or wind, which depend on weather, tidal energy is foreseeable years in advance. We know exactly when tides will occur, exactly how strong they'll be, making tidal power one of the most reliable forms of renewable energy. Yet there's something beautifully circular about returning to tides as an energy source. We began by observing tides, learning their patterns, adapting our lives to their rhythm. Now we're discovering that the same ancient force that fed our ancestors can power our future. But this return to tidal energy also carries responsibility. Tides aren't just physical phenomena, they're the heartbeat of coastal ecosystems. Harnessing tidal energy without disrupting marine life requires careful planning and environmental awareness. Yet despite all our technology and understanding, the ocean remains more powerful than human infrastructure. Coastal communities still must respect the tides, still must plan around them. Every major port in the world operates according to tide schedules. Container ships time their arrivals to coincide with high tides when channel depths are sufficient. Naval operations account for tidal conditions. Even in the age of GPS and sophisticated weather forecasting, the tide remains a force that commands respect and adjustment. And now, as global climate changes and sea levels rise, our relationship with tides is entering a new phase. The tides themselves aren't changing. Gravity still operates according to the same laws, but the baseline water level is rising, which changes how tides interact with coastlines. High tides reach higher, low tides don't retreat as far, and storm surges that occur during high tides become catastrophically more severe. Coastal communities that have existed for generations are beginning to experience flooding during tides that never posed problems before. This is the human tide. The ways we've learned to live with the ocean depend on it and increasingly affect it. We've built magnificent harbor cities, created global trade networks, developed technologies to harness ocean energy. But we've also altered ocean chemistry through carbon emissions, changed marine ecosystems through overfishing and pollution, and are now confronting the reality that our actions have consequences that return to us in the form of rising seas. The ocean, patient and powerful, is responding to what we've done. And perhaps that's the final lesson of the tides, that everything is connected, that actions have consequences, that the forces shaping our world operate according to principles larger than individual human lives or even than human civilization. The moon still pulls, the tides still rise and fall, but the details of how those tides interact with coastlines, with ecosystems, with human communities are changing. And how we respond to those changes will shape the relationship between humanity and the sea for generations to come. As we draw near the end of this journey, one truth remains. The ocean was here long before us and will be here long after. Its mysteries will persist. Its depths will remain largely unexplored. Its power will continue to shape coastlines and climates. We are temporary visitors, brief witnesses to forces that operate on timescales that dwarf human history. And perhaps the wisest response is simply to pay attention, to learn, to respect what we cannot control, and to remember that we are part of this system, not separate from it. The tide is turning, as it always does. The question is whether we turn with it, adapting our presence on this planet to acknowledge both the ocean's gifts and its limits. The same moon that has guided sailors for millennia is still there, still pulling, still creating the ancient rhythm that connects Earth to the cosmos. And in that rhythm, if we listen carefully enough, we might find wisdom for navigating whatever comes next. That we return now to where we began, standing at the edge of the ocean, watching moonlight silver the water, listening to the whisper of waves advancing and retreating with patient, eternal rhythm. But you understand now what you're witnessing. You see beyond the surface to the invisible threads connecting moon and tide, connecting gravity and water, connecting the celestial and the terrestrial in an embrace that has persisted for billions of years. The ocean is breathing. It has always been breathing. It will continue breathing long after this night, long after this life, long after the brief flicker of human civilization has passed into whatever comes next. There's profound comfort in that continuity, in knowing that some rhythms are so fundamental, so woven into the fabric of reality, that they transcend the temporary concerns of any single species or moment in time. Think about what you've learned tonight, that the tides are pulled by the moon, influenced by the sun, shaped by hidden underwater topography, that countless species have synchronized their lives to these rhythms, built their survival strategies around the predictable rising and falling of water, that humans, too, have organized civilizations around tides, learned to read their patterns, developed technologies to harness their power. That beneath all this, beneath the understood science and explored ecosystems, the ocean still harbors mysteries, trenches unmapped, creatures unknown, sounds unexplained. This knowledge doesn't diminish the wonder, it deepens it. Understanding gravity doesn't make the moon less beautiful. Knowing about bioluminescence doesn't make the deep ocean less magical. Science, properly understood, is a form of attention, a way of looking more closely at the world and discovering that it's stranger, more intricate, more breathtaking than we imagined, and the ocean rewards attention. Every time we look, we discover something new. Every expedition into unexplored waters returns with surprises, species that shouldn't exist, ecosystems operating on principles we didn't anticipate, evidence that life is more adaptable, more persistent, more creative than we give it credit for. The ocean is still teaching us, still showing us new possibilities, still expanding our sense of what's real and what's possible on this planet we call home. As you rest now, as your breathing slows and deepens, let it synchronize with the rhythm of waves. Let the tide's ancient pulse become your pulse. Let the knowledge that you're connected to these forces, that the water in your body responds to the same moon that moves the seas, become a source of peace rather than merely information. You are part of this, not separate from it, watching from outside, but woven into the same fabric of matter and energy and gravitational attraction that binds the universe together. The tide is rising somewhere right now, falling somewhere else. Barnacles are opening their shells as water returns, extending delicate feeding appendages into the current. Hermit crabs are timing journeys back to deeper pools. Ghost crabs are emerging from burrows to hunt along the water's edge. Coral reefs are preparing for spawning, synchronized to lunar phases by mechanisms we're only beginning to understand. Bioluminescent creatures in the deep ocean are producing their own light, communicating in languages we can't yet read. And the moon, that pale companion that has circled Earth for over 4 billion years, continues its patient,